Back with example 8 of the lesson, what is a limit here? We have a piecewise function that we are in charge of sketching again. This time though, there's 3 pieces. And if we look at the restrictions over on this side, it looks like -1 is going to be an important point, or we might break off into branches, as well as +1. So those are important values of x to note. So let's start with the top branch again. So if x is less than or equal to -1, then f at x is equal to -x minus 2, which we should recognize as a straight line. We are allowed to sub -1 in. So if we did that, we would get -1 minus 2, which would just be 1 minus 2, or -1. And that's going to have a closed-in dot because we're allowed to sub -1 in. And then anything smaller than -1 as well, we're allowed to put in. So like -2, which would give us 0, -3, which would give us 1. And we do know that this is a line with a slope of -1, so we can fill it out, draw it in, arrow towards this way, because we can keep putting values less than or equal to -1 in. And there's our first branch done. The next part of the function is only valid between -1 and 1, but x is not actually allowed to equal -1 or 1. So we could pretend to put -1 in, but we're going to have an open circle there, and f at x is just equal to x. So we would come here at -1, -1 ready to put an open hole, but there's already a closed hole here. So closed hole trumps open hole. We're actually on the graph at that point. Then we're allowed to put anything in between -1 and 1 in, so like -0.5 and -0.5 is okay. 0 and 0 is fine, part of our graph. All the way we can pretend to put 1 in, but we're going to have an open circle there. So that's the next portion of our graph, straight line there. Then we have x is greater than or equal to 1, so again we're allowed to put 1 in. So that's going to give us 1 squared minus 2 times 1, which is -1. And that's going to be a closed-in dot because you're allowed to put 1 in. If we put 2 in, we would get 2 squared minus 2 times 2, or 4 minus 4, which is 0. So 2 and 0. If we put 3 in, 3 squared minus 2 times 3, 9 minus 6, which is 3. So at 3, 1, 2, 3. And if we see an x squared, we do realize that that's going to be quadratic or parabolic in nature. So we could draw in that branch of the curve as well. So we've drawn our function f at x. And they're interested in knowing the limit as x approaches -1. So as x approaches -1, for the limit to exist, the limit from the left and the limit from the right would have to equal each other. And the limit from the left would be on this branch, approaching the value -1. The limit from the right would be on this other branch, but also approaching -1. So the limit from the left and right are equal. So we can say the limit exists, and it equals -1 in this case. Also, we're interested in the limit as x approaches 1 of f at x. So if we analyze here, if we have the limit from the left, we'd be on this branch here, corresponding y values, approaching 1. And if we approach 1 from the right, our corresponding values would be down here on this branch. So we'd be approaching -1. So that means since the limit from the left and right are not equal, the limit as x approaches 1 does not exist. It is said that the graph of y equals f at x is continuous at x equals -1 and discontinuous at x equals 1. What do you think is meant by this, and how does it relate to limits and calculus? So if we look at our graph here, we had our closed dot and then we put an open dot over it, but the closed dot fills the open dot. So we can see that the function is continuous here. There's no gaps. Okay, so that is what continuous means, but it also means that the limit is equal to the value that both sides are approaching here. Okay, but continuous really means that there's no gaps or holes. Discontinuous then at x equals 1, you can see that there's a hole and a gap, okay? So that we're discontinuous at x equals 1. All right, and that concludes our lesson on what is a limit.